Hi, welcome. Today we are joined by Jaike van Twiller, a postdoc from IT University of Copenhagen. His work focuses on operations, machine learning, and optimization under uncertainty. In this interview, we are going to talk about his research on navigating demand uncertainty in container shipping, deep reinforcement learning for adaptive and feasible master storage planning. Can you tell me a little bit more about yourself and how you actually got interested in this field?
Sure. So, like you already introduced, I'm a postdoc at the IT University, but I have a background in operations research and AI methods. So, before I went to Denmark, I actually did a master's in Eindhoven University of Technology. And there, it's interest for just, I would say, logistics started because the master was operations management and logistics. And then I had the opportunity while I was searching for a follow-up job or a PhD to work with Rune Mulle Jensen and Georgia Grubic at the IT University. And they opened the world of maritime logistics and container shipping for me. And after that, I got so interested that I thought, well, might as well stay a bit longer.
Could you tell me more, please? What is actually a master storage planning and why is it so complex?
Yeah, of course. So, master storage planning, or maybe let's say first regular storage planning, is about to decide where containers go on the container ship. So you literally say, okay, this container goes to that specific location, and we fit it over there. Master storage planning is more saying, okay, if we have a container, we can assign it to a general area on the ship where there's maybe hundreds different of locations where it can exactly be stored. And then you make it more of an approximate plan where your capacity goes. So that is useful because it simplifies the problem a little bit, but still you need to consider that the ship stays stable, that it is efficient to be loaded and offloaded, and that you also deal with things like uncertainty in demand, because dealing with uncertainty in demand is inherently quite complicated. So all these things together, and actually many more, because I'm just highlighting a few, those actually make the problem quite hard to solve. But in the end, we try to find a way to assign as much cargo to the already going container ship, because a container ship is basically going from port to port like a bus line, and we want to make sure that this bus or container ship is as filled as possible when it is going to sail.
What are some of the rules or limitations that planners need to follow?
Yeah, that's a good point. I think that goes more into the detail than what are the detailed rules and constraints. And yeah, like I said, safety is very important. So safety comes in different forms. For instance, you want to make sure that the ship is stable. It should not capsize or break, because it could also break under certain stress forces. So you have to make some physical hydrostatic computations and make sure that it is within a certain safety margin to make sure that it will not create these foundational problems. But in addition to that, you can also think about just general capacity. So you have literally the size of a container and where does it fit in like this big container ship. So where do you place it? Below deck, above deck? How broad or how high are the containers and how much space is there left? So that is something to think about. But also the weight of the container. So you cannot put too many heavy containers on top of a stack because a stack might fall over. And this is also a very topical issue that we see a lot when you have certain stress forces on a stack on board that actually containers fly off in the middle of sea. And this is of course things that you want to prevent. And of course there's the efficiency part. So we also need to consider how do we distribute certain containers at certain times during a port rotation. So you maybe put a lot of the same containers in the same locations, on the same larger locations, but then you also need to offload them all at the same time, which is actually difficult for key cranes because you have key cranes operating on the ship at the same time, and they actually want to make sure that these are efficiently balanced in their workload. So there's more efficiency things to consider.
Mm-hmm.
And finally, also the maybe from the stower planner's perspective is that every time the ship sails from a new port to a new port, they need to have a new plan ready before the port arrives or before the ship arrives at the port. So that's also an important consideration.
Why is actually demand uncertainty such a central challenge when it comes to planning container storage?
No, that is mostly due because you have what we call the uptake managers, and the uptake managers, they make a decision on how much container should approximately go to what container ship, and then we have the stowage planners who deal with the actual situation. And between that expectation and the actual situation are huge differences. So sometimes bookings don't show up, sometimes last minute bookings are added.
Mm-hmm.
So that means that there's inherent uncertainty in the demand of these containers. And this changes at the last second, and that makes it that we really need to consider how uncertainty affects our plans, because having suddenly way more containers to load, whereas there's way too little capacity for it, that will cause a lot of costs on the transporter side, because they need to then say, sorry, we don't have capacity for you, even though you booked on our side.
Mm-hmm.
Or they're not using all the capacity well enough, and then the ship is actually not using its full capacity, which is then costs from their side. They could have loaded up more. And this also taps into sustainability, because if you could load it up more, the overall carbon footprint of one container jumps up.
Yeah. Why is this feasible projection part so important when creating a good storage plan?
So that taps into the rules I talked about before, because you like deep reinforcement learning is an AI method, and AI methods are quite good at making an approximate, good enough solution to some things, but it's not very good at inherently making sure that all these rules and constraints are completely adhered to.
Mm-hmm.
So if you do not have this layer on top, it basically would violate a lot of safety risks or a lot of inefficiencies or maybe capacity related issues. So that's why this projection layer is important to make sure that we shave off the unrealistic, unsafe parts of a solution.
How is your method actually different from traditional planning methods that shipping companies have been using before?
That's also a very a very topical thing, I would say. So generally, I would classify certain methods in three categories. There's a lot of nuances in between, but for now, for the sake of argument, let's keep it at three categories. You have more exact methods. So these are actually quite. They try to find like the best possible solution according to math. And this has good benefits, but sometimes also the drawback that it's slow, because it tries to find the perfect solution. And especially when you deal with uncertainty here, this is actually quite problematic because it takes even longer. Then you have AI methods, which are very fast, but very approximate. As I said before, you need some extra layer to make sure it's feasible, but they're very fast, and they can actually build some sort of model of reality inside these neural network models, and that makes them very good with dealing with uncertainty. And then in the middle, you have also more traditional heuristic methods, and they give you some guarantee. So they can tell you, okay, maybe we get this performance, but it's probably not the best performance, but it takes more time than the AI methods. So I think like these are the three flavors. And for this project, we believe that speed was of the essence, and getting a good enough solution that might outperform these methods on certain scenarios. And that's also what we showed in our experiment.
So in practical terms, how can shipping companies benefit from your research?
That's a good point. I think what they could really see from this research is that uncertainty is a really important part in planning for container shipping in general. So what we also show in our experiments is that you can assume a situation where you have perfect information, and then you get maybe very high profits for that situation, but that's very unrealistic. because you don't know the future. Then you can actually create a situation in which you just say, okay, so we do not know the future, so we cannot count on the future. So we can only decide for where we are now, and then we can make some expectations, but we cannot anticipate these future steps yet. And that gives a more of a lower bound of profits that you can get. And in the middle is what we proposed, is you can anticipate the future a little bit with some statistics based on what you think you might know about the uncertainty. And this is where you show that, okay, this value of information, actually, because more information helps you getting higher profit by anticipating the future. But what these uncertainties are, you never exactly know, but it's better to anticipate some uncertainty than none at all.
Yeah.
And I think that's an important takeaway, that uncertainty is here and we need to find a way to deal with it. And it's better to have some version of uncertainty included in your model than not including it at all.
Can your solution work for different kinds of ships, roads, or cargo types?
Yeah, that's also a fair point. It works for different types of voyages, so different routes. It works for different cargo types. It doesn't work yet for different types of ships as we have it right now. So that means that we trained it, and that trained model can work on different port rotations, voyages, and can work on different cargo types. But if we want to make it usable for another ship, we need to retrain it. And that's not a major issue, but for making it even more useful directly, we are considering also being able to make it flexible for multiple ships. And that's something that we have in the pipeline to.
So that's actually a future step.
Exactly,
Okay.
exactly.
Could this model also help reduce emissions or improve sustainability?
Definitely, yeah. I think one major thing here is that container ships are very, very huge, and that makes them very, very useful actually for reducing greenhouse gases, because many, many products are shipped every day across the world. And it works best if we use these container ships as much as possible, because like we discussed before, the average footprint of one container drops significantly. You can imagine if you only ship 100 containers on a 10,000 container ship, that's very inefficient. This will in real life not happen, but of course you can also imagine it's being half full opposed to it being almost completely full. And that's where you want to make sure that it is as full as possible, and also then dealing with uncertainty is a big part on making sure that it's as full as possible. So this is how I believe this research can definitely benefit reducing the carbon footprint of container shipping.
Could you tell us a little bit more about the challenges that you faced during the research?
Sure. I think it's going to be a bit of a technical talk here, is that when you're dealing with AI models, you actually try to train them, and that is something that happens through a process called differentiation. And this generally happens on GPUs, which are nice and fast. But because we use differentiation, you have a limitation in certain types of mathematical operations that you can do. So sometimes you think about a very nice layer that you want to include at the end of your AI model, but then you cannot differentiate through that. So that means that basically, if you try to do some sort of solution prediction, then if you try to then learn from that solution prediction, it cannot back propagate the values. So it cannot learn from the update, basically. And that's a major technical challenge. And what that then was an issue for us is that we need to figure out how can we make this feasibility projection layer so that it's differentiable, but also tries to actually solve the constraints that are realistic in real life. So it was a bit of a technical meets reality match here that we needed to try to overcome. And I believe we have done that nicely for a specific set of constraints, which are mostly convex constraints to go in a bit of a technical term. But there's also non-convex constraints out there, and there is still a challenge for us to see if we can improve this layer to include more types of constraints that are actually very realistic, but we cannot include right now.
So actually, what improvements or next steps would you like to explore in the research?
Yeah, that's always good to think about the future. Like I mentioned before, I think the dealing with different ship sizes and also trying to deal with these non-convex constraints could be very nice. But there's more to it, because now we use what we call an end-to-end model. So it gets input and it tries to create a solution, which is a stowage plan. But you can also think about what if we use an AI model on top of maybe an existing heuristic model. So we had these three classes before, the exact, heuristic, and AI model. And you can also use these AI models to speed up these heuristic models and also these exact models, actually. So yeah, these we call hybrid models, and we are actually considering how can we use hybrid models for the future and maybe see how we can speed up operations and get more performance guarantees, so to say.
Do you think that this kind of planning tool could be used in real shipping companies soon?
A very relevant question, I would say. I would say we are not quite there yet. We need to consider the fact that certain types of planning tools have a lot of like proven worth to container shipping companies. And right now we are with the AI models more in a phase where we say, okay, hey, we have a proof of concept. This works under certain situations for certain types of constraints with simulated data. How can we now move this towards maybe completely realistic data and this being applied in live operations? And to make that happen, we need help. We need more access to data. We need to be able to show that it also works on completely realistic data. But at the same time, yeah, we also need to make the model more able to deal with all the real life considerations that exist in real container shipping.
Could you give an estimation of how much time we will need in order to implement this research into real life?
That's that's always a nice one to come up with estimations. I like to refrain from saying, hey, we can solve this within 3 years and then we're completely done. I believe there's a lot of issues on the horizon that we could not anticipate yet. So exactly, uncertainty, and also in the research landscape. So I hope that we in maybe 10 years can get something that's actually very useful in real life, but that doesn't mean that we get in 10 years a model that can replace a human. Not at all. I feel like the future is probably more of a decision support model that is very smart, but also a human that is there in the loop to check whether this all works very well. So I believe this can speed up the whole process that we have right now, but it shouldn't fundamentally change it, because with all maybe the existing issues that you can see with things like ChatGPT and other large language models, is that they sometimes tend to hallucinate. And this is some fundamental problem also in our AI models, that we cannot always guarantee that it's completely 100% safe in all scenarios. And this is, of course, very, very important in container shipping. So we need to have some oversight and some people that are there to say, okay, this is a good enough idea, we can work with this, but we need to make sure that we are the final say in the matter. And that makes it, again, very uncertain for me to say, when do we get something that is working great? Maybe we go into a situation where we can wait another 100 years again. You never know.
What's the most important takeaway you would like the maritime industry to remember from this research?
That AI methods are here to stay. They are here and are very useful. So try to embrace them. Try to see how they can benefit your current operations. Maybe they can do smaller things than solving the major problems that we, for instance, now looked at. And also see that if they try to solve easier versions of these major problems, how that can still maybe benefit the stowage planners, the other planners. There's way more different types of problems than this can be applied to. So I believe that there's many ways AI methods can help, and they're very good at uncertainty and very fast. So that's always a very good selling point, I would say, to the industry.
That were our questions for today. Thank you so much for joining us and to sharing your knowledge and your information on your research.
Yeah, of course.
Yeah,
Yeah.
thank you.
Thank you.